Go over Unit 7, and for this video specifically SCP 5. So I'm going to do all the SCPs. I'm going to start off with SCP 5 because people have been requesting that. But yeah, let's just get started. I'm going to go through the entire packet. I'm going to go through all the key concepts we learned, and hopefully we're prepared for that test tomorrow. And practice some of the SCP 5 stuff too. But yeah, I'm just going to talk about some of the key ideas. So, rotational energy. That was the first key idea, concept, and really the thing with rotational energy is conservation of energy, right? So if we have something like, a pulley or whatever, you want to, if you're trying to find the final speed, you can use conservation of energy, right? Because there's no outside forces, and that, all the UG of this, so it's initially all UG, it's going to transfer into the K of the little mass. And then so if this is M and this is big M, then there's also going to be that K rot, rot or whatever, I don't care. K rotational for the pulley. So this was like a new thing, K rotational. I don't like just giving equations because it's on the equation sheet, but I think it's important to note that K rotational is just 1/2 I omega squared. So yeah, there you go. Rotational energy. One neat thing you can do is for a problem like this, right? Let's say you have a derive. You're trying to derive V in terms of, all your other variables. So when you start doing your MGH business, and then your 1/2 MV squared and all that stuff, there's gonna be that, so let's just say K rotational I. So for your omega, we don't want omega in our final derived equation, so we can once again use that bridge equation. Instead of omega squared, we can do V squared over the radius squared, all right? So there you go. And then radius squared, right? Because we're squaring the whole fraction. One thing to keep in mind, so what's really nice then is that when you have I, so your rotational inertia equation, let's just say this is a hoop, right? So hoop is mr squared. You can then plug in your mr squared and you're going to see that, the r's cancel out. This is on the practice test, so I thought I might mention it. For the practice test, they had a problem very similar to this, but the pulley, like it was, the disc was like this, and then there was a pulley, right? So when you're going to bridge over, if this is r, this is going to be r, right? The rotational inertia part. But then remember, for our bridge equation, we have to do what links it. We have to use the r, which links the rotational motion and the linear motion. What do I mean by that? I mean that you have to use this, like if it's 1/2, you have to use this 1/2 because that's where the linear stuff connects with the rotational stuff. One way to think about it is if you did one full rotation, right? It's gonna use less rope, it's gonna fall less, right? So you can't, like if you were to do distance equals theta r, if you have less r, right, less distance. So that's what links it. And if you use this big pulley, you need a lot more distance or like rope, right, to fall, and then you're gonna have a bigger r, and then it's the same theta. Just some things to keep in mind about bridge equations. Don't get lazy with that. I think other than that, this was pretty much it in terms of rotational energy. Just using conservation of energy for deriving, for solving for sure. I'm going through the packet to see if there's anything else. Really not. Just based on rotational energy, I'm not getting a whole lot of SCP-5 just flipping through. So I'm going to go over to angular momentum. So that's rotational energy. Angular momentum. This is where a lot of the math is heavier. So the first thing we learned is that L, so the angular momentum of any object, is going to equal its rotational inertia times omega. Very similar to, so this is like the rotational version. This is very similar to P, momentum, is equal to M times V. We're doing all rotational version. So there you go. On the test, you might have to use some linear momentum stuff. I know in the pivots we've been doing that, but really focus on this, right? We're focusing on rotational momentum. And the nice thing about it is that it is conserved. So it is conserved when there are no outside torque nets. I should probably write this a little bit bigger. I just noticed it's quite small, but like L equals I omega. This was one central equation. And we learned, similar to impulse, that the change in L is equal to torque net times time, right? Torque net causes a change in angular momentum. So if there's no torque, your angular momentum is not going to change. Here's a big key thing. I think we've been talking about this a lot, is that rotational inertia can change. You pull your arms in, you pull your arms out. You can do all sorts of things. So you can't just say, okay, L stays the same, so omega doesn't change. Because L can stay the same, but if you pull your arms in, right, we've dealt with this. So if we're doing something like, let me get this. If we're doing something like L initial equals L final, right? L initial, so let's say it's for something spinning and then your arms are out. You're going to do inertia initial, or rotational inertia initial, times omega initial is going to equal omega final times, rotational inertia final times omega final. So, if your rotational inertia goes up, in order for these two to be the exact same, right, your omega final needs to go down. Try to understand that. Don't memorize if rotational inertia goes up, omega goes down. That's not always true. For example, if you think about when there is an external torque, your I could stay constant and then your omega does go up. So this doesn't change, but this goes up because you have a torque net. When there's no torque net, so I'm going to kind of write this, when there's no torque net, angular momentum is conserved. And this is pretty powerful. This is really powerful. You can handle a lot of problems when momentum is conserved, because you can take a look at, like, okay, collisions, angular collisions. And I'm going to actually kind of go into angular collisions now, which is going to talk about point mass stuff and all that stuff. But yeah, this is what angular momentum is great for. You can it's conserved like in a lot of in all collisions really, so you can use it. So let's take a case, right? We have a door. Let's do it like this. We have this cool little door as a we'll just say like a length of R. L, let's just use L, right? Oh, that's angular. Okay, let's do lowercase l. And it has a mass, and we have a ball being chucked right at it with the speed of v. So, things to keep in mind. This, for the whole system, so for both these systems, there is angular momentum. How do we know that, right? Because the ball is moving straight. How do we know there's angular momentum? How do we know that ball has angular momentum? Because after the collision, right, if they stick together, well, they will stick together, even if it doesn't. I mean, really, what's going to happen is when the ball hits, it's going to start rotating. So if you have L initial equals L final, there's going to be L final. We know that things are going to start rotating when they collide. So there has to be L initial for the whole system. That has to be true. Conservation of angular momentum. There's no outside torque. Okay, so the kind of big idea is that this has angular momentum, even though it's moving straight. We can calculate this. How can we calculate this? L is going to equal I times omega. L is going to equal, for point mass, it's mr squared. And they'll give that to you on the thing. And then the omega is v over r. Take a look. This r squared, the squared cancels out with this bottom r. You get L is equal to mRv. Now, one thing to keep in mind, this is the angular momentum for a point mass. I hear a lot of people say this is the rotational inertia equation. No. We use the rotational inertia equation to get this. This is not the rotational inertia equation. You also have to keep in mind it's going to be that perpendicular. So if you have this distance as r, then this v is not all contributing to it, right? Because there's going to be a perpendicular component. So if we draw this better, there's going to be that perpendicular component and that parallel component. The perpendicular component is what contributes, I guess, to the angular momentum. So the nice thing is, as it gets closer and closer, right, the distance is smaller, but the perpendicular velocity, the perpendicular component gets bigger. And you can imagine right here, it's all perpendicular. So that's how the L stays the same. Because even though R decreases, the perpendicular component will increase even if the speed is the same. So yeah, things to keep in mind. If there's an explanation or mathing, that's just something to keep in mind, right? Use the angle. So it's going to be L equals mv r sine theta. This is the theta. Okay, cool. Hopefully that makes sense. I want to go over the big ideas first, and then if there's any like just some problems to keep in mind, I'll do it. Okay, so let's just go more in depth with collisions. For all collision problems, you can use that. Do not use energy. Do not use energy. That's gonna not be good, because we know mechanical energy transforms into sound, heat, deformation, a lot of nasty things. I don't know. I think that has to do with entropy, but I don't know much about thermodynamics. So, but yeah, what I'm trying to get at is that energy will be lost, or quote unquote lost. Use angular momentum. So if you have something like, so this is a problem on a quiz. If we had a platform, and then so it was spinning with an initial speed, and then we drop a little smaller mass. Okay? Some things to keep in mind is that the smaller disk is not spinning initially, it doesn't have angular momentum. So, and obviously it's like, around the, it's dropped, and afterwards they're gonna both start spinning. So if we draw sort of that after, they're both spinning now. Like so, they're both spinning speed w. Okay, if we want to figure out like what is the omega, right? What is the rotational inertia of the small disk? What's the rotational inertia of the big disk? You would use conservation of angular momentum. We know L initial equals L final. We know that what was I gonna say? Oh yeah, we know that for initially it's gonna be, so if this is big and this is small, all the angular momentum initially is here, because this is the only thing spinning. We're going to do IB times omega initial equals. So now we have to add up the two angular momentums. So we're going to have IB, which is unchanged. Nothing about the rotational inertia of B changed. B is still the same disk. And then we'll do omega final plus I small omega final. Once again, now it's spinning. These are spinning at the same speed, so you can actually factor out the omega. And what this does for us is kind of treat it as one object. We can say IB plus I small times omega. Okay, so think it through, right? This kind of makes sense. They're sort of rotating as one object. You can almost sort of add up the rotational inertias because they have the same omega final. And then from here you can solve for any of these variables if it's like a derivation or if they give you something. And then on the test they'll also tell you like, oh, IB is 1/2 mr squared or whatever. So that's not a worry either. So yeah, cool. You have stuff like that. Same thing goes for like a door, right? We have the L initial, L final. Literally start every problem with that. And then you can figure out, okay, the only thing that has angular momentum is a bullet. So we'll do mvr. You don't need to worry about perpendicular because right at that instant, it's going to be all perpendicular. It's going to equal, what is it going to equal? It's going to equal then the I of the bullet, which is just mr squared, plus I of the door times omega, because they're going to be rotating at the same speed. If the bullet bounces back, then you just do, okay, mvr, same thing, is going to equal ib omega minus, right? We're doing minus, right? Yeah, we're doing minus mvr, and then we'll do like a v naught, right? So if it bounces back, it's in opposite direction. Like this is going to rotate this way, this is going to go back. It's in opposite directions. We use a minus. Yeah, honestly, to be honest, that might be the majority of SEP 5. I'm trying to think what other things do we need to keep in mind. Yeah, I think that's it. It's really just using conservation of angular momentum, using rotational energy when appropriate. Do not use it for collision. How long is this video? 16 minutes. Okay, I might just end it here. I hope that covers the basics. Just remember conservation of energy to do stuff like this. Or conservation of angular momentum to do stuff like this. Remember conservation of energy when you have stuff with like pulleys, right? Because we know there's no, energy lost. Yeah, should be the bulk of it. Yeah, alright, thank you for watching. I'm going to do SEP 4 and 6 pronto.